talk about position and velocity. Namely, let's take what we saw in lab number 1, as well as what some of the homework you guys have already started on in homework 2. This will help clear up some of the stuff in the lab homework as well. Okay, so let's start off. Oh, one more thing, just a little reminder, it just hit me. When you do the lab homework, a lot of the questions will look like the same questions that are in the back of your lab book, where it says homework 1, 2, 3. What I did was I transcribed most of the questions that I'm interested in. I transcribed them into WebAssign. That means you don't have to turn in anything by way of paper. All the answers will be put in through WebAssign, will be graded through WebAssign, okay? Now, some of the questions will say, what does the graph look like if you move this way? What you need to do, put your initials on the graph, on the axes that you see in the lab book, draw the graph, snap the picture, upload it into WebAssign. Everything make sense? Okay, just a heads up though. I have to manually grade everything, which means even though you'll see a score, it doesn't mean anything until I've actually graded everything. I got a question, yes? As long as I get initials, I want to see initials, okay? Because what I do not want, because I'm thinking like a student, thinking like a quote-unquote clever student, what I do not want is the same picture over and over and over again across multiple students. That kind of violates the spirit of things, doesn't it? Okay? All right. Everything makes sense? And remember, the homework is going to be due Wednesday morning, so you got to attack it as soon as we can. We got another question.
One of the graphs on the homework assignment, like the one that had the U shape, looked like it had some like alterations to it than what was in the book. Have you referred to the book picture for that, or referred to the picture right on?
Considering the fact that I scanned those pictures from the book, those should be the same. So if you got a question, come see me and I'll clear it up, okay? All right. Any other questions about that? That's a legitimate question there, okay? Just to repeat, because it's a video going. The question is, if there's a difference between a picture in the WebAssign versus a picture in the book, which one do we use? And they should be the same. If they're not, come show me, okay? All right, let's go ahead and jump into this. We're going to talk about position and velocity. We had definitions of position and velocity already. One of the things we've got to do is we've got to define the ever-popular question, where am I? Where are we? We need to define the location. Way back when, we got to establish location. Way back when, it wasn't that long ago, you found out you were going to go to college. Of course, you and all your buddies found out you were going to go to college. One person's going, I'm going to Alabama. One person, I'm going to Georgia. One person, I'm going to Penn State. You know, going to really some good schools. And every time they say that, you know, okay, not a problem. When they came up to you, you say, yeah, I'm going to college too. And they said, what did they ask? Where are you going to college? And you said, Marion Military Institute. To which point, what did they say? Why? No. Where? Where is Marion Military Institute? That's what they all asked, right? Among the other questions, that certainly was one of them. How did you tell them where MMI was? Middle of nowhere. Doesn't work. Yes? Okay. Okay, so what you said is it was at a certain position from direction from Birmingham, certain direction from Selma. A number of you may have used different types of statements, but they were all pretty much the same thing. Specifically, you had to have some kind of reference point. Okay, you had to have some kind of reference point to base it on. In addition, once you have the agreed upon reference point, for example, if you're talking to your buddy and you're saying, well, it's near Birmingham, okay, now I've got the reference point, but that doesn't give you enough information, okay? Because you need the direction from Birmingham. Well, it's to the southwest of Birmingham. Okay? Well, so's Mobile. And so's Cancun. Those are all southwest of Birmingham. Well, those sure ain't Marion Military Institute, are they? So there's one more piece of information you need, which is not time, although we certainly can use time to do this. Distance, that's correct. We certainly, especially if you grew up in California. Okay, everything is measured in Southern California, especially. Everything is measured in driving time. My answer, you take a look at how far is it between UCLA and USC? Well, it's 15 miles on the road and an hour and a half on the freeway. Because anybody who's ever driven on Interstate 10 in that stretch knows what I'm talking about. Anyway, what I'm trying to get at is you need two pieces of information, don't you? You need a reference point that you can measure from. You need a direction that you're going to measure from. And you need the distance. In lab number 1, what was our reference point? The motion sensor, okay? The motion sensor measured distance, didn't it? But if we had the motion sensor in the middle of the room, put the motion sensor in the middle of the room, we could measure distance to the back of the room if it was facing to the back of the room, but don't we have a bunch of positions toward the front of the room that we need to measure as well? Okay, so direction needs to come into play as well. Now let's talk about distance real quick. Let's talk in terms of two-dimensional distances. We could even talk three-dimensional distances, but we'll start with two-dimensional distances. Our definition of distance is going to be the length of the path that you travel. Really easy. Take the meter stick, start flipping it over and over and over along the path that you're going to travel. Okay? For example, how long is the 400-meter race? We're talking standard track here. So how long is the 400-meter race? 400 meters, one lap around, exactly right. The distance that the runner runs is going to be 400 meters. This is assuming lane number 1. All good? If I did the mile, or if I did the 1,600 meters, how long is the 1,600-meter race? Well, for everybody then, it's going to be 1,600 meters, because everybody's starting on the same line and finishing on the same line, right? Okay, that's the distance, that's the path. How far is it from here to Tuscaloosa? It's about an hour drive, but the thing is, the direction, the path you travel is going to tell you how far you're going to travel. Are you going to take Highway 14 west, then pick up 69 north? Or are you going to take Highway 5 north and then take 82 west? Two different paths, two different lengths to get from the same positions, from Marion to Tuscaloosa. You following along? Okay. Displacement, however, is different. Displacement is the change in position. Displacement is, I started in Marion, I ended up in Tuscaloosa. How far did I travel? I don't care about the path. All I care about is where did I start and where did I end up. You could think of it as the crow flies. Does that make sense? If we're talking about on the 100-meter track, for example, okay, well, yeah. So we're going to define displacement as the change in position. It's the difference from the final position to the starting position. On a one-dimensional line, like a 100-meter track or something, real simple. XF minus XI, XF standing for final position, XI standing for initial position, is equal to delta X, the difference of X, the change in X. Okay? So what is the displacement of the 400-meter race? 0, exactly right. You went nowhere. Or rather, you ended up where you started out at. 1,600-meter runners. Where did you end up at? 0 displacement. You went nowhere fast. It's even more depressing for the 10,000-meter runners. Right? I want you to run 6.2 miles, but end up at the same point. I'll give you an example, a little bit of an aside. Tokyo Olympics, the marathon, 26.2 miles. 26.2 miles that they had to run. That was the distance they ran. The displacement was somewhere around a mile and a half, because they had to do a couple of loops and the finish line ended up at a different place than the starting line. Think that's bad. What's even worse was the 50-kilometer walk. 42 miles that they had to race walk. Okay? And their displacement was 0. Because the finish line was at the same place as the starting line. They had a 2-kilometer loop that they had to do 25 times. Now, for those of you who look at me, why are you doing that? Because it's a race walk, you've got to have judges. Because the judges are judging the form of the walkers. Okay? If they don't follow the rules, they can get ejected. Could be worse, because back when I was younger, they used to do this on the 400-meter track. Can you imagine doing 50 kilometers on a track? I had a tough enough time doing a 5-mile time trial on a track, so 50 kilometers on a track would be a bear. So back to the topic at hand. What is the displacement of the 400-meter race? The answer is 0, because you end up at the same point you start at. Here's another one. If a person goes from the 60-meter mark to the 40-meter mark, again, standard track, what is the distance traveled? You guys should be able to do this off the top of your heads. What's the distance traveled? 20 meters. What's the displacement? Negative 20 meters, because we're going to take those positions, plug them into the delta x formulation. So it would be 40 meters minus 60 meters to give us a delta x of negative 20 meters. Direction is important for displacement. Okay? 20 meters, 100 meters versus negative 100 meters is the difference between winning the race and looking like a fool. Right? Because if you're running a 100-meter race and you go positive 100 meters, you're going to the finish line. If you go negative 100 meters, you end up outside the stadium. Right? Okay. Now, speaking of races, how much time does it take to change position? It's not going to be instantaneous. Okay? We have not invented teleportation yet. So therefore, it's going to take a certain amount of time to change the position. We've got two names for that. We've got speed and velocity. Here's my definitions. Speed, average speed is defined as the distance that is traveled divided by the time interval. How far did you travel along your path divided by how long it took for you to travel that path? So that's where we get the times for the mile on the track, the times for the marathon, the time for the 50-kilometer walk. Path dependent, the actual distance, or rather the distance you moved. Okay? So far, so good? So if we've got something that involves distance, then shouldn't we have something that involves displacement? Well, yeah, that makes sense. And so we get average velocity. And the definition of the average velocity is the displacement divided by the time. Divided by the time interval, I should say. That is to say, what is the change in the x position divided by the change in the time? Now, many times our change in time can be read directly off of a watch because we're assuming that the starting time is going to be 0 with our stopwatches. But that's not always the case. For example, how old are you? That's a time interval, isn't it? In order to figure out the time interval, you have to determine what is today's date and subtract from it the date you were born. And that gives you the time interval called your age. You see where we're going here? So it's not always the number you read, because you never know if there was a number you had to start with. It's path independent. We don't care how you did it. We don't care how you got from Marion to Tuscaloosa. All we care about is that you got to Tuscaloosa. Actually, well, reality, we do care, but that's beside the point. Okay? So my question for you is, what is the average velocity if you go from 0 meters to 100 meters in 10.5 seconds? 0 meters to 100 meters in 10.5 seconds. Yes? 9.5 meters per second. I got to stress this. If you give me a number, then you're incorrect. You've got to give me the units as well. Okay, so 9.5 meters per second. That makes sense. A little less than 10 meters per second. Okay, how about this one? What's the average velocity if you run the 400 meters in 55 seconds? 0 meters per second, exactly right. Because what's your displacement? 0. You ended up at the same place you started at. So the average velocity, your velocity over the entire time, turns out to be 0. But what's your average speed? 7 point what? 7.3 meters per second. Yeah, I can forgive, by the way, a little bit of a side. I can forgive an extra decimal place on the precision. Okay, I can forgive an extra decimal place. But we can't go farther than that. All right? All right, so, yeah, it's about 7.5. Now I got a task for you guys. Whiteboard tasking. Whiteboard tasking means that you get together in your little groups, okay? You get the whiteboards out, and you do the task. In this particular case, the task is make a velocity versus time graph based upon this motion. Make a velocity versus time graph based upon this motion. Now, I would venture you 4 working together, you 4 working together, you 3 working together. Okay, let's go with you 3 and then you 4. Okay? So go ahead and start working that one out. Remember lab number 1? Maybe you'll be able to figure it out. First of all, walking around, most of you got the right idea. Most of you got the right idea that what you need to do is you need to make a plot of the slopes of each of those lines through each time segment. Now, what am I talking about here? Well, we have to remember from lab number 1, how would I make this graph? We see for the first second, or for the first 2 seconds, what am I doing? Not moving, standing still, that's correct. Then for the next 2 seconds, I'm moving away from the motion sensor. Then what happens for the next second? Stand still, that's correct. How do you know I'm standing still? The position is not changing, that's correct. The slope of that line is what? 0. You're starting to get my hint here, okay? Most of you got it, but we'll discuss it, that's okay. Let's talk about this for a second. On a position versus time graph, what you see on the position versus time graph, that any change in position will be along the vertical axis. So when you go from 1 meter to 4 meters, that plus 3 meters is going to be a rise on the y-axis, isn't it? The change in time is going to be a change along the horizontal axis. From 1 second to 3 seconds is going to be a run, if you will. So delta x, the change in position, is the rise. Delta y, or delta t, the change in time, is the run. Therefore, the average velocity is the slope on a position versus time graph. Now, on that particular graph, we saw a number of different slopes because the velocity is going to change. The motion changes at different points in time. But you can still calculate the average velocity between those changes, between where the motion changes. I hope I was, yeah. Okay, so average velocity is the slope on a position versus time graph, but if I want to know what my velocity is right now, I've got to take a look at a point on that position versus time graph and make a line tangent to that point. And that's going to give me the instantaneous velocity. Another way of looking at it, let's make the time interval very, 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 very small, like 1/100th of a second. If the line is straight in that time interval, then you've got essentially the instantaneous velocity. Again, depending on your scale. If you're measuring in minutes and you got 1/100th of a second, that's pretty much of a moment, isn't it? But if you're measuring in millionths of a second, and your interval is billionths of a second, that's not necessarily that big. You know, that's only a 1% interval. Okay, so I told you this on Wednesday. Quotients can be seen as slopes. If I want to do a division, I put the rise on the x-axis or the y-axis, I put the run on the x-axis, and then I find the slope of that line, and that will give me my quotient. You with me? So let's talk about this particular graph here. From 0 to 2 seconds, what's the slope of that line? 0, correct. From 0 to 2 seconds, we have a straight line. Now, from 2 to 4 seconds, 1.5 what? Meters per second. That's correct, because we have a rise of 3 meters. The displacement is 4 meters minus 1 meter. Final position minus initial position. Our time interval is 2 seconds, so it becomes 3 meters divided by 2 seconds, so that gives us 1.5 meters per second. What is the slope from 4 to 5 seconds? 0, correct. Straight horizontal line, not changing position. The velocity is 0. What about from 5 to 6 seconds? 2 meters per second. The displacement, we're going from 7 meters, it's 7 meters minus 5 meters, which gives us a displacement of 2 meters per 2 meters. Okay, last one, 6 to 7 seconds. Negative 5 meters per second. Negative 5 meters per second, because we're going to go, the delta x equation is going to be the final position minus the initial position. 1 meter minus 6 meters, which is negative 5 meters. And then we divide that by the 1 second, which gives us negative 5 meters per second. Thus, we get a velocity versus time graph that looks like that. You see where we're going here, guys? Question from the lab. What's the difference? How do you know that an object is moving at a constant velocity on a position versus time graph? Because it's not a flat line. If it's moving at a constant velocity on a position versus time graph, how can you tell? Yes? No? Yes? Excuse me? No. A constant slope. A constant slope. A line with a constant slope is a constant velocity. Thus, the first 2 seconds, a constant velocity of 0. The second 2 seconds, a constant velocity of 1.5 meters per second. Okay? How can you tell on a position versus time graph that the velocity is changing? The position graph will curve. Okay? That was questions from the lab, yes? All right, so here we got our, so as you can see, given this particular graph, we would expect to see a series of straight lines, wouldn't we? Of straight horizontal lines for the velocity graph, because the velocity isn't changing except at specific points. With me so far? Okay, exercise number 2. I'm going to give you a velocity versus time graph. Let's go the other way. Here's my velocity versus time graph. If an object is starting at the 1 meter mark, what does the position versus time graph look like? Object starts at the 1 meter mark, and you're given this velocity versus time graph. What does the position versus time graph look like? Okay, guys. Given this velocity versus time graph, what's your position versus time graph? There's 2 ways we can go about doing it. One way we can go about doing it is remembering that the slope of the position time graph gives us the velocity. Since we're starting at 1 meter, all we have to do is take a look at the velocity versus time graph. We see we've got a velocity of 2 meters per second for the first 2 seconds, right? That means we just start at the 1 meter mark and draw a line with a slope of 2 meters every second for 2 seconds. Then we draw a line with a 0 slope for the next 2 seconds. And then we draw a line with a negative 1 meter slope for every second. So just by doing that, we can do it that way. Cool. But I want to show you another way of doing that as well, which is, and I keep pushing the button, which is this. First, we start off with our definition of average velocity, which is change in the x position divided by the time interval, delta x over delta t. Now, I have to give you a trigger warning here. I'm about to do some algebra. Okay, so don't be frightened. I'll walk you through it. All right, I've now done some algebra. In this particular case, all I did was multiply both sides by delta t, and so I get a product that says that the change in my position, my delta x, is going to be equal to my average velocity multiplied by the time interval. This is an equation that you guys have used all the time. Every time you go driving any real distance, you're using that equation, aren't you? Okay. Now, if we look on a velocity versus time graph, then what we see is if we have velocity here and if we have time here, then this height right here represents the velocity. And then if we go to this point right here, this distance represents the time interval, if the velocity versus time graph looked like that. So what is v multiplied by t, delta t, going to give me? Okay, that's on the equation, but on the graph, it's going to give me an area. So the area is going to represent the change in position. So we see that by the equation, the change in position is equal to average velocity times time. So if I represent it on graph, the area underneath a velocity versus time graph gives me the change of position. It does not tell me where I start, and it does not tell me where I end, but it will tell me where I have to go. How far and in what direction. You following along here, guys? Multiplications, products, are represented as areas. That's my little geometric lesson from Wednesday. Change in position is equal to the area under the velocity versus time graph. Okay, so if we take a look at this, what's the area underneath the first segment? 2 times 2 meters per second, which gives us 4 meters. Okay, so that area is 4 meters. What's the area under the 2 to 4 seconds going to be? Nope. From 2 to 4 seconds, what's the area here? 0, correct. So there's no change in position in that time interval. And then what's the area underneath the 4 to 6 second mark? -2. What that means is you're going to change your position -2 meters. You're going to move 2 meters towards the origin. Knowing that, since you know so your total change of position is going to be 2 meters, right? The 4 meters out minus the 2 meters back, which means my total change of position is now 2 meters. Take the total area, and I've got the displacement for the entire motion. This is similar to a football player running out. He catches the pass, he runs forward, then he jukes back, and then he gets tackled. What's his total change in position? What's the total displacement? It's how far he went forward minus how far he came back, right? Okay, I love football. It's great for physics for this kind of motion because football is a one-dimensional game played on a two-dimensional surface. Wouldn't you agree? We don't care about how far side to side goes. The game depends upon how far the ball is advanced or comes back. Okay, let's move on. So the final position ends up being 3 meters because the initial position was at the 2 meter mark. Everything make sense? Okay. Why do you get that? Because you get this graph. Does this graph look like your graphs? It should, because you all kind of did it right. You start at 1 meter. You end up at 5 meters at the end of 2 seconds because you advanced 4 meters. You stayed still for 2 seconds, and then you came back over 2 seconds, and you ended up at the 3 meter mark. Your change in position was only 2 meters. Everything make sense? All good? This should help you out on the homework in WebAssign, on the lab homework. Now again, some reminders. The lab homework in WebAssign are many of the questions that are transcribed from the lab book. There are no papers to turn in. I will not accept any paper entries. Okay? You answer the questions in WebAssign. If it asks for a graph, every question where it's asked for a graph, there is a graph for you to draw onto in your lab book. All you need to do is snap a picture of it and upload it. Again, the instructions say make sure you initial put your name on it. Okay? Again, because I don't want to see the same picture over and over again, I want everybody to upload their own stuff. All right? If you have any technical issues, please come see me, send me an email, I'll see what I can do. I will be here on campus until the end of the day, even after the festivities if you got some questions. The homework is due on Wednesday, so that means you could ask me questions on Tuesday afternoon. Please don't wait until the last minute to do this stuff, okay? That's all I got for you guys. I will see you guys on the parade ground.